Welcome back, students. Today we'll be learning the concept of buoyancy. Now, what is buoyancy? Now, the concept of buoyancy or buoyant force, it is applicable for fluids. We need to know what are fluids. The substances which can flow easily are called fluids, and these fluids exert pressure on the container in which they are kept. A fluid can be liquid or gas, and it exerts pressure in all directions, even upwards. The upward force which is acting on an object when it is immersed in a fluid, it is known as buoyant force, or one more name is there, that is known as upthrust. Now, the buoyant force, that is only responsible for making heavy objects seem lighter when it is completely immersed in water. Now, what causes this buoyant force? Whenever an object is immersed in a fluid, two forces are acting on it. One is its weight in the downward direction, and the second one is buoyant force in the upward direction. Now, we can refer to the second diagram. We are considering a mug filled with water immersed in a bucket containing water. Now, water exerts force on the sides of the mug as well as on its top and bottom. The sideways forces exerted by water on the mug being equal and opposite at a particular depth, they are balancing each other. So there is a net force of water acting on top of the mug which acts in downward direction, and a force of water acting on the bottom of the mug, and it is acting in upward direction. So all the forces which are acting sidewise are balanced. We have two forces which are shown with two red arrows in the diagram. But we know that when we are going to the deeper region in a fluid, the fluid pressure or lateral pressure increases, because lateral pressure is given by the formula H rho g, where rho is the density. So more is the depth, more will be the lateral pressure. So in this case, we can say that F1, the downward force F1, that is equal to P1 into A, that means pressure into area, and lateral pressure is H1 rho g into A, because at that height, lateral pressure will be H1 rho g. So in the second position, the force is F2, which is equal to P2A, that is equal to H2 rho g into A. The depth of the container, the lower bottom part of the container, is H2. And we can see from the diagram that H2 is greater than H1. So obviously H2 rho GA will be greater than H1 rho GA. That is, we can say that F2 is greater than F1. So F1 and F2 are two forces which are acting against each other. So the net force in vertical direction should be F2 minus F1, because F1 is having greater value. So there is a net upward force on the mug acting, which is equal to the difference in the upward force and the downward force. This net upward force acting on the mug is known as buoyant force. Now we'll be discussing about Archimedes principle. When an object is wholly or partially immersed in a fluid, it experiences a buoyant force or upthrust, which is equal to the weight of the fluid displaced by the immersed object. We need to learn and remember the statement of Archimedes' principle. So it works on a fully or partially immersed object. Even the gases exert an upward buoyant force on the object placed in them, because we discussed in the previous slide that fluid means both liquids and gases. But in most of the cases, it is so small that we usually ignore that amount of buoyant force. It is the buoyant force due to the displaced air which makes a balloon rise in air. Now, what are the factors which is affecting buoyant force? The magnitude of buoyant force exerted by a fluid depends on two factors. One is the volume of the solid immersed in the fluid. More is the volume of the solid, more will be the volume of the fluid displaced. So, more will be the weight of the displaced fluid or buoyant force. The second one is density of fluid. More is the density of fluid, more will be the mass and weight of the displaced fluid. And according to Archimedes' principle, we know that weight of the displaced fluid is equal to buoyant force. So, more will be the weight or density, the buoyant force will increase. Now, we will be solving some numerical problems on buoyant force. Question number 1. When an aluminium object is immersed in water, it displaces 5 kg of water. How much is the buoyant force acting on the aluminium object in newtons? Here, small g is equal to 10 meter per second square. According to Archimedes' principle, the buoyant force acting on this aluminium object will be equal to the weight of the water displaced by this aluminium object. Here, mass of displaced water m is equal to 5 kg. Acceleration due to gravity small g is equal to 10 meter per second square. Weight of displaced water is equal to mass of displaced water into g, because weight is equal to mg. So, buoyant force will also be equal to mg. We are substituting the values of m and g as 5 and 10, and the buoyant force will be 50 Newton. Question number 2. When a boat is partially immersed in water, it displaces 600 kg of water. How much is the buoyant force acting on the boats in newtons? G is equal to 10 meter per second square. According to Archimedes' principle, the buoyant force acting on this aluminium object will be equal to the weight of the water displaced by the object. Here, mass of displaced water m is equal to 600 kg. Acceleration due to gravity g is equal to 10 meter per second square. So, weight of displaced water is equal to m into g, where m is the mass of displaced water. So, we are substituting the value 600 into 10, that is 6000 Newton. Now, we will discuss what is apparent weight loss. It's our common experience, we all have experienced that when a mug filled with water remains immersed in the bucket full of water, it appears to be light and hence easy to lift. But as soon as the mug filled with water is lifted out of the bucket of water, it feels much heavier. So, when immersed in water, objects appear to lose some weight. The word apparent says that it is not an actual weight loss. It is losing its weight apparently as long as it is immersed in the fluid. This is because when an object is immersed in a fluid, there are two forces acting on it. What are the two forces? One is the force of weight, which is acting in the downward direction towards the center of earth, And the second force is buoyant force, which is acting in the upward direction due to the displaced fluid. Now, these are the two forces which are acting in opposite direction. So, because of this upward buoyant force, the effect of weight is reduced, and this phenomenon is known as apparent weight loss. Now, how can we measure apparent weight loss? It is equal to the weight of the object in air minus the buoyant force. Now we'll discuss the principle of flotation. We have already seen in the last slide that when an object is partially or fully immersed in a fluid, two forces are acting on it. One is the downward force of weight and one is the upward force of buoyancy. Now, whether an object will float or sink in a liquid or in a fluid, it will depend on the relative magnitudes of these two forces. Now, let us consider one object of mass small m, which is having a volume of capital V and it is immersed in a fluid. It displaces V volume of fluid because its own volume is V. So it will displace equal volume of fluid. Now let us consider that the fluid which is displaced, that is having volume V, which is equal to the volume of the object, but the mass is different because it is assumed that mass of the immersed body is small m and mass of the displaced fluid is m dashed. Note that the immersed object and the displaced fluid has same volume but different masses because their densities are different. Now we'll discuss case 1. If the buoyant force or upthrust exerted by the fluid is more than the weight of the object, that means the upward force is more than the downward force. Obviously, we know that the body will try to move up because the upward force is more. But why? We know that from Archimedes' principle that buoyant force is measured by the weight of the displaced fluid. And we know the formula for weight is m into g, mass into acceleration due to gravity. We have assumed that the mass of the displaced fluid is m dashed. So, weight of the displaced fluid or the buoyancy will be equal to m dashed g. And weight of the immersed body is mg because m is the mass of the immersed object. Now we are cancelling small g from both sides. We are getting m dashed is equal to m. Now we are dividing both sides of the equation by capital V because both the thing like the immersed body and the displaced fluid has same volume because an object is displacing equal volume of fluid. So we are dividing both sides by V and m by V gives us the density. Mass by volume is equal to density. So d dash is equal to d. That means if the density of the object is less than the density of the fluid, then the body will rise in the fluid and it will float. Let us take an example. Densities of iron and glass have less than density of mercury. So weight of these objects will be less than the buoyant force exerted by mercury. So they float in mercury. Similarly, densities of cork, wood and ice have less than the density of water. So weight of these objects will be less than buoyant force exerted by water. So these objects will float in water. Now we will discuss case 2 where the buoyant force or upthrust is less than the weight of the object. So similarly, B is less than W, and if we follow the same steps as before, then the density of the fluid will be less than the density of the immersed body in this case. We can see in the picture, in this case the upward force is less than the downward force. So the body will try to sink down because the force towards its bottom will be more. Let us discuss few examples. Densities of iron, glass, aluminium and mercury have more than density of water. So weight of these objects will be more than the buoyant force exerted by water. So they sink in water. Case 3. If the buoyant force or upthrust is exactly equal to the weight of the object. This is a very rare case where buoyant force is equal to W. So we can deduce that d dashed is equal to d. That means density of the fluid and the density of the immersed body will be same in this case. So in this case the body will float inside water and no part of it remains above the fluid. One example of this case is Pyrex glass. It floats inside the glycerin and no part remains above. Why ships float? We have seen that the iron nail, it sinks in water. But the ships are also made of iron. Why does it float? When we put a piece of iron in water, it sinks immediately because iron is denser than water. Ship is not a solid block of iron and steel. A ship is a hollow object made of iron and steel which contains a lot of air in it. Air has very low density, and due to the presence of lot of air inside its chamber, the average density of the ship becomes less than the density of water. We have discussed in the previous slides that when the density of the immersed body is less than the density of the fluid, then the body floats. So for floating a ship, we have to make a chamber such that it is filled with air, and the average density of this air chamber and the body of the ship becomes less than the density of water. So a heavy ship floats because it displaces a large weight of water, which provides a great buoyant force to keep it afloat. So there are two reasons due to which a ship floats. Let us discuss a few more questions. A half kg sheet of tin sinks in water, but if the same sheet is converted into a box or a boat, it floats. Why? The average density of hollow box or boat made of sheet of tin becomes less than the density of water because of the presence of air. Next question. An iron nail sinks in water but floats in mercury. Why? Density of iron is more than density of water. So the weight of the iron nail is more than the buoyant force exerted by water. So iron nail sinks in water. But density of iron is more than density of mercury. So the weight of iron nail is less than the buoyant force exerted by mercury. So iron nail floats in mercury. Now we'll discuss what is density. Density means how much substance is there in a particular space. Density of a substance is defined as the mass per unit volume. So we can write it in a formula: density is equal to mass of the substance by volume of the same substance. SI unit of density is SI unit of mass divided by SI unit of volume. SI unit of mass is kg and SI unit of volume is meter cube. So SI unit of density is kg per meter cube. In SI unit, density of water is 1000 kg per meter cube, and in CGS unit, the density of water is 1 gram per centimeter. In your book, you will see that there is a table where densities of many substances are provided. You need not learn those values. Only you remember these two values, that density of water in SI unit is 1000 kg per meter cube, and in CGS unit the density of water is 1 gram per centimeter cube. This slide is very important for doing numerical problems. In the previous slide we have seen that SI unit of density is 1000 kg per meter cube, and CGS unit the density of water is gram per centimeter cube. But how to do this conversion? We know that SI unit of density is kg per meter cube, and we also know that 1 meter is equal to 100 centimeter. Now 1 meter cube means 1 meter into 1 meter into 1 meter. So we can write that is equal to 100 centimeter into 100 centimeter into 100 centimeter. So 1 meter cube is basically equal to 100,000 centimeter cube. That means 10 lakhs centimeter cube makes 1 meter cube. Now 1 kg per meter cube can be written as 1 kg by 1 meter cube. So instead of 1 kg we can write 1000 gram, and instead of 1 meter cube we can write 10 lakhs centimeter cube. After reducing we are getting 1 by 1000 gram per centimeter cube. If we do cross multiplication, we will be getting that 1000 kg per meter cube is equal to 1 gram per centimeter cube. We can write in power notation that 1000 kg per meter cube, we can write it as 10 to the power 3 kg per meter cube is equal to 1 gram per centimeter cube. Let us do some numerical problems on density. The mass of 2 meter cube of steel is 15,600 kg. Calculate the density of steel in SI units. Mass M is equal to 15,600 kg and volume V is equal to 2 meter cube. We will use the density formula, that is equal to mass of the substance by volume of the substance. Substituting the values, we get 15,600 by 2, that is 7800 kg per meter cube. Question number 2. An object of mass 50 gram has a volume of 20 centimeter cube. Calculate the density of the object. If the density of water is 1 gram per centimeter cube, state whether the object will float or sink in water. Mass M is equal to 50 gram, volume V is equal to 20 centimeter cube, density is equal to mass by volume. So 50 gram by 20 centimeter cube, that is 2.5 gram per centimeter cube. Since the density of the object is greater than the density of water, which is equal to 1 gram per centimeter cube, we are comparing the densities and we are deciding that the object will sink in water because the density of the object is more than density of the fluid. Now we'll discuss about relative density. Relative density is defined as the ratio of density of a substance to the density of water. So basically, we are trying to find out that how much heavier is a particular substance with respect to same volume of water. So the formula for relative density will be density of the substance by density of water. Now what will be the SI unit of relative density? We can see from the formula that it is the ratio of two densities, density of substance and density of water, and both the density have same unit kg per meter cube, which gets cancelled, and as it is a perfect ratio, it does not have any unit. Let us do few numerical problems on relative density. The relative density of silver is 10.8. Note it that there is no unit written with it. If the density of water be 1 into 10 to the power 3 kg per meter cube, calculate the density of silver in SI unit. We'll write down the formula. Relative density is equal to density of substance by density of water. So 10.8 is equal to density of substance into 10 to the power 3 kg per meter cube. By doing cross multiplication, we can get that density of silver will be equal to 10.8 into 10 to the power 3 kg per meter cube. Here, we'll observe something very interesting. That means if we are given with the density of a substance in CGS unit, that means in gram per centimeter cube, if we directly multiply that value with 10 to the power 3, we'll be getting the density of the same substance in SI unit, that is in kg per meter cube. The volume of a solid of mass 500 gram is 350 centimeter cube. What will be the density of the solid? We'll use the formula for density, mass of the substance by volume of the substance. Substituting the values, we are getting density is equal to 500 gram divided by 350 centimeter cube. If we calculate, we'll be getting 1.42 gram per centimeter cube. In the second part, it is asked that what will be the mass of water displaced by the solid. The solid will displace water equal to its own volume. So volume of the solid will be equal to volume of displaced water. That is equal to 350 centimeter cube. Now they are asking for mass. We found the volume. Now we'll use the same formula for density. Density is equal to mass by volume. In the previous part, we have considered the density of the solid, but here we'll use the density of water. So density of water is in CGS unit 1 gram per centimeter cube. Why we are choosing CGS unit here? Because the volume of water is given in CGS unit, that is centimeter cube. So we are choosing this value. Substituting the values, we are getting 1 gram per centimeter cube is equal to mass of solid by 350 centimeter cube. By cross multiplication, we are getting that mass of solid will be equal to 350 gram. Part C, they are asking for relative density. The formula is density of substance by density of water. Density of substance we already found in part A, 1.42 gram per centimeter cube, and density of water is 1 gram per centimeter cube. So we are getting relative density is equal to 1.42. In part D, it is asked that whether the body will float or sink in water. How will we do that? We have to compare the density of the substance with density of water. If it is more than the density of water, it will sink. If it is less than the density of water, it will float. Here in part A, we found that density of the substance is 1.42, which is more than 1 gram per centimeter cube. So the object will sink and settle down in water. Question number 5. The relative density of a substance is 7.1. What will be its density in SI unit? Relative density is equal to density of the substance by density of water. 7.1 is equal to density of substance by density of water in SI unit. We are choosing SI unit because in the question it is asked to find out the density of the substance in SI unit. So we are choosing the value 1000 kg per meter cube for density of water, not 1 gram per cc. So density of the substance will be obtained by cross multiplying 7.1 into 1000, that is 7100 kg per meter cube. Question number 6. The density of turpentine is 840 kg per meter cube. What will be its relative density? The formula is density of turpentine divided by density of water. Density of turpentine is 840 and density of water is 1000. Why we are choosing 1000 kg per meter cube, not 1 gram per centimeter cube? I think by now everyone could understand. Here the density of turpentine is given in SI. So for comparing that, we are choosing the density of water also in SI unit, not in CGS unit. Otherwise, we cannot compare. While comparing two quantities, we have to bring them to same unit. Otherwise, the comparison does not have any meaning. So, 840 divided by 1000, that is equal to 0.84. Question number 7. A piece of steel has a volume of 12 centimeter cube and a mass of 96 gram. What is its density in gram per centimeter cube and in kg per meter cube? So once we have to find out in CGS unit and then we have to convert it into SI unit. Mass M is equal to 96 gram. Volume V is equal to 12 centimeter cube. Density of steel will be mass by volume, so 96 by 12, that is 8 gram per centimeter cube. Now we know that when we are converting density from CGS to SI unit, we have to multiply with 1000. So density of steel in SI unit will be 8 into 1000, that is 8000 kg per meter cube. Question number 8. The density of gold is 19 gram per centimeter cube. Find the volume of 95 gram of gold. Mass M is equal to 95 gram. Volume V is equal to 19 centimeter cube. So that volume of steel is equal to 95 gram divided by 19 centimeter cube, that is equal to 5 centimeter cube. Question number 9. What is the mass of 5 meter cube of cement of density 3000 kg per meter cube? So here volume is provided and density is provided. We have to find out the mass. Volume V is equal to 5 meter cube. Density V is equal to 3000 kg per meter cube. We'll use the same formula. Density is equal to mass by volume and we will substitute the values. 3000 is equal to mass by 5. So mass of substance is equal to 3000 into 5, that is 15,000 kg. Question number 10. When a golf ball is lowered into a measuring cylinder containing water, the water level rises by 30 centimeter cube. When the ball is completely submerged, if the mass of ball in air is 33 gram, find its density. So rise of water level in measuring cylinder must be equal to the volume of the submerged ball. So volume is 30 centimeter cube because the water level rises by 30 centimeter cube. Mass is given, small m is equal to 33 gram, both in CGS unit. So we are using the formula for density, that is mass by volume. So it will be 33 by 30, that is 1.1 gram per centimeter cube. Now what are the learning outcome of this part of the chapter? Students will be able to know about the phenomenon of buoyancy. They will know about the factors affecting buoyant force. They will be knowing about the Archimedes principle. They will be able to solve numerical problems on calculation of buoyant force. They will be knowing about the apparent weight loss. They will know and verify the laws of flotation. They will know the concept of density. They will know about the concept of relative density. And they will be able to solve numerical problems based on density and relative density.